Calculating the fill capacity of a cable tray involves determining the maximum number of cables that can be safely and effectively installed within the tray's dimensions. For a 24-inch wide ladder cable tray and type TC10-3 cables, your initial calculation is correct. You can fit approximately 18 TC10-3 cables based on a diameter of 488 inches per cable, resulting in an area of 1.532 square inches per cable and a tray capacity fill of 28 square inches. The calculation is 28 square inches divided by 1.532, equaling approximately 18 cables. The tray may appear empty even with the calculated number of cables. This is because it's generally advisable to maintain some free space within the cable tray. This empty space allows for future expansion, enhances airflow to prevent overheating, and facilitates easier cable installation and maintenance. Remember that specific designs and manufacturer specifications influence the fill capacity of the cable tray. Firstly, consider utilizing a cable tray with an increased fill capacity. These trays are designed to accommodate a larger number of cables within the same physical dimensions. Secondly, multiple layers of cables can be installed within the same tray, provided that cable supports or dividers are employed to maintain separation between the layers. Thirdly, installing 2 or more ladder cable trays side by side creates multiple cable paths, effectively multiplying the available space for cable installation. Fourthly, explore the possibility of using alternative cable types. Smaller diameter cables or flat cables occupy less space, enabling the installation of more cables within the same tray. When installing cables in a cable tray, it's crucial to adhere to the manufacturer's recommendations and applicable codes and standards. Overfilling the tray or exceeding the specified fill capacity can compromise the integrity and safety of the installation. It is important to maintain the proper bending radius of the cables to prevent damage. This may require additional spacing between cables. Always consult the National Electrical Code, or NEC, for relevant articles pertaining to cable tray installations. Article 392 covers cable trays, and it provides detailed requirements for installation, allowable fill, and other important considerations. Specifically, NEC 392.22 addresses the allowable cable fill for cable trays. This section outlines the permissible amount of cable that can be installed in a cable tray based on the type of cable and the construction of the tray. NEC 392.22 covers cable trays containing only conductors rated 2000 volts or less. The sum of the cross-sectional areas of all cables in the tray shall not exceed the maximum allowable cable fill area, as indicated in Table 392.22a. For ladder or ventilated trough cable trays, the maximum allowable cable fill area for cables rated 2000 volts or less is dependent on the cable tray width. For example, a 6-inch wide ladder cable tray has a maximum allowable cable fill area of 6 square inches, while a 12-inch wide ladder cable tray has a maximum allowable cable fill area of 12 square inches. For solid-bottomed cable trays, the maximum allowable cable fill area is less than that of ladder or ventilated trough cable trays. NEC 392.22b covers cable trays containing multi-conductor ventilating power and control tray cables type MV. The sum of the cross-sectional areas of all cables in the tray shall not exceed the maximum allowable cable fill area, as indicated in Table 392.22b. NEC 392.22c covers cable trays containing single-conductor cables. The sum of the diameters of all single-conductor cables in the tray shall not exceed the cable tray width. Other NEC articles may also be relevant to cable tray installations depending on the specific application. For example, Article 310 addresses conductors for general wiring, and it provides requirements for conductor ampacity insulation and other important considerations. To determine the ampacity of conductors installed in cable trays, refer to NEC 310.15, which covers ampacity calculations for conductors rated 0 to 2000 volts. Table 310.15b3 provides adjustment factors for more than 3 current carrying conductors in a raceway or cable. When conductors are installed in cable trays, these adjustment factors may need to be applied to the conductor and capacity to account for the effects of heat buildup. NEC 392.30 covers cable tray installation requirements, including grounding and bonding. Cable trays must be properly grounded and bonded to ensure electrical safety. This helps to minimize the risk of electric shock and equipment damage. NEC 392.60 addresses cable tray construction requirements. Cable trays must be designed and constructed to withstand the anticipated loads and environmental conditions. The trays must also be properly supported and secured to prevent movement or displacement. Always refer to the latest edition of the NEC for the most up-to-date requirements and guidelines. Cable tray installation should be performed by qualified personnel who are familiar with the NEC and other applicable codes and standards. The diameter of a 10-3TC cable is approximately 0.488 inches. This is the outer diameter of the cable, including the insulation. The cross-sectional area of the cable can be calculated using the formula for the area of a circle, which is pi times the radius squared. The radius is 1/2 of the diameter. Therefore, the radius of a 10-3TC cable is 0.244 inches. The cross-sectional area of the cable is 3.14 times 0.244 squared, which equals approximately 0.187 square inches. The fill capacity of a cable tray is the maximum amount of cable that can be installed in the tray. The fill capacity is typically expressed as a percentage of the cable tray's cross-sectional area. The NEC specifies the maximum allowable fill capacity for cable trays. For ladder cable trays, the maximum allowable fill capacity is 50% for cables rated 2000 volts or less and 75% for cables rated over 2000 volts. The fill capacity of a cable tray can be affected by a number of factors, including the size and type of cable, the spacing between cables, and the presence of other equipment in the tray. To calculate the fill capacity of a cable tray, follow these steps. Firstly, determine the cross-sectional area of the cable tray. This is the area of the tray's opening. Secondly, determine the cross-sectional area of each cable that will be installed in the tray. Thirdly, calculate the total cross-sectional area of all the cables. Fourthly, divide the total cross-sectional area of the cables by the cross-sectional area of the cable tray. Fifthly, multiply the result by 100% to express the fill capacity as a percentage. To install more cables in the cable tray, firstly, consider using smaller diameter cables. Secondly, space the cables more closely together. Thirdly, remove any unnecessary equipment from the tray. Fourthly, use a cable tray with a larger cross-sectional area. Fifthly, install a second cable tray parallel to the first one. In addition to the NEC, there may be other applicable codes and standards that govern cable tray installations. These codes and standards may vary depending on the location of the installation. It is important to consult with a qualified electrical engineer or contractor to ensure that the cable tray installation meets all applicable requirements. It is very important to consider voltage drop, which is the decrease in voltage that occurs along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can cause equipment to malfunction or not operate at all. The NEC specifies the maximum allowable voltage drop for branch circuits and feeders. For branch circuits, the voltage drop should not exceed 3%. For feeders, the voltage drop should not exceed 5%. The total voltage drop for both branch circuits and feeders should not exceed 8%. Voltage drop can be calculated using the following formula: voltage drop equals current times impedance. The current is the amount of current flowing through the conductor, and the impedance is the opposition to current flow. The impedance of a conductor depends on its resistance and reactance. The resistance is the opposition to current flow due to the conductor's material and size. The reactance is the opposition to current flow due to the conductor's inductance and capacitance. To minimize voltage drop, firstly, use larger conductors. Larger conductors have lower resistance, which reduces voltage drop. Secondly, shorten the length of the conductors. Shorter conductors have lower impedance, which reduces voltage drop. Thirdly, use conductors with lower reactance. Conductors with lower inductance and capacitance have lower reactance, which reduces voltage drop. Fourthly, reduce the current flowing through the conductors. Lower current reduces voltage drop. Fifthly, use voltage drop compensation equipment. Voltage drop compensation equipment can boost the voltage at the end of a long conductor run, which compensates for voltage drop. Short circuit current is the amount of current that flows through a circuit during a short circuit fault. A short circuit is an unintentional connection between two or more conductors that have different potentials. Short circuits can be caused by a variety of factors, including damaged insulation, loose connections, and accidental contact with conductive objects. Short circuit current can be very high, often thousands of amps. This high current can cause severe damage to equipment and can also be a fire hazard. The NEC requires that all electrical systems be protected against short-circuit currents. This protection is typically provided by overcurrent protection devices, such as circuit breakers and fuses. Overcurrent protection devices are designed to interrupt the flow of current when a short circuit occurs, which prevents damage to equipment and reduces the risk of fire. The available short-circuit current at a particular point in an electrical system depends on a number of factors, including the size of the utility transformer, the impedance of the conductors, and the presence of other equipment in the system. To determine the available short-circuit current at a particular point in an electrical system, firstly, obtain the short-circuit current rating of the utility transformer. Secondly, calculate the impedance of the conductors from the transformer to the point in question. Thirdly, calculate the impedance of any other equipment in the system that may contribute to the short-circuit current. Fourthly, use the following formula to calculate the available short-circuit current. Available short-circuit current equals transformer short-circuit current divided by the square root of the sum of the squares of the impedances. It is important to consult with a qualified electrical engineer or contractor to ensure that the electrical system is properly protected against short-circuit currents. The grounding and bonding of cable trays is essential for electrical safety. Grounding provides a low impedance path for fault current to flow back to the source, which helps to trap over current protection devices and prevent electrical shock hazards. Bonding connects all metal parts of the electrical system together, which helps to equalize the voltage potential and prevent electrical shock hazards. The NEC requires that all metal cable trays be grounded and bonded. The grounding and bonding requirements for cable trays are specified in Article 392 of the NEC. Cable trays must be grounded to a suitable grounding electrode, such as a grounding rod or a metal water pipe. The grounding conductor must be sized in accordance with NEC Table 250.122. Cable trays must be bonded to each other and to other metal parts of the electrical system, such as metal conduit and equipment enclosures. The bonding conductors must be sized in accordance with NEC Table 250.102. The grounding and bonding connections must be made using approved methods, such as listed grounding and bonding fittings. It is important to ensure that the grounding and bonding connections are properly installed and maintained. Loose or corroded connections can compromise the effectiveness of the grounding and bonding system. Cable trays should be inspected regularly to ensure that the grounding and bonding connections are in good condition. If any problems are found, they should be corrected immediately. Qualified personnel should perform grounding and bonding of cable trays. The NEC requires that all electrical work be performed by qualified personnel who are familiar with the NEC and other applicable codes and standards. Cable support is also essential for cable tray installations. Cable trays must be properly supported to prevent them from sagging or collapsing. The NEC specifies the requirements for cable tray support. Cable trays must be supported at intervals not exceeding the manufacturer's recommendations. The supports must be strong enough to support the weight of the cable tray and the cables installed in it. The supports must be securely fastened to the built-in structure. Cable trays should be supported using approved methods such as cable tray clamps, hangers, and brackets. It is important to ensure that the cable tray supports are properly installed and maintained. Loose or damaged supports can compromise the integrity of the cable tray system. Cable trays should be inspected regularly to ensure that the supports are in good condition. If any problems are found, they should be corrected immediately. Qualified personnel should perform cable tray support. Cable installation practices are also very important in cable trays. Proper cable installation practices are essential for ensuring the safety and reliability of cable tray installations. The NEC specifies the requirements for cable installation in cable trays. Cables must be installed in cable trays in a neat and workmanlike manner. Cables must be supported at intervals not exceeding the manufacturer's recommendations. Cables must be protected from damage. Cables must be properly identified. Cables must be installed in accordance with the manufacturer's instructions. It is important to ensure that the cables are properly installed in the cable tray. Improperly installed cables can be damaged or can cause damage to the cable tray. Cable trays should be inspected regularly to ensure that the cables are properly installed. If any problems are found, they should be corrected immediately. Cable identification is very important, and cables and cable trays must be properly identified to prevent confusion and to facilitate maintenance and troubleshooting. The NEC specifies the requirements for cable identification. Cables must be identified with permanent markers or labels. The markers or labels must be legible and durable. The markers or labels must identify the cable's function and voltage. Cable identification should be consistent throughout the cable tray system. It is important to ensure that the cables are properly identified. Improperly identified cables can lead to confusion and errors during maintenance and troubleshooting. Cable trays should be inspected regularly to ensure that the cables are properly identified. If any problems are found, they should be corrected immediately. Cable maintenance and inspection are also crucial for cable trays. Regular maintenance and inspection of cable trays are essential for ensuring the safety and reliability of the electrical system. Cable trays should be inspected regularly for damage, corrosion, and loose connections. The cables should be inspected for damage, wear, and tear. The support should be inspected for damage and corrosion. The grounding and bonding connections should be inspected for corrosion and looseness. Any problems that are found should be corrected immediately. Cable trays should be cleaned regularly to remove dust, dirt, and debris. Cable tray maintenance and inspection should be performed by qualified personnel. Always consult with a qualified electrical engineer or contractor to ensure that the cable tray installation meets all applicable requirements and is performed in a safe and workmanlike manner.